All right, hello discrete math. We are now in the third part of chapter 13. So in this chapter about Fibonacci numbers and the golden ratio, we're now going to start to see where these numbers show up in a geometric sense. And this is going to be the study of what are called gnomons. So to start off with, gnomons, most common usage of that word is to describe the pin of a sundial. So when you're thinking about a gnomon, think about a sundial, and we'll see a better picture than this in a moment. But think about the middle of a sundial, what's used to tell the time, looks something kind of like this. That's going to be what we're going to be talking about today, which are what are called gnomons. The original Greek meaning of that word is one who knows. So yeah, not all that surprising that we'll find that in our study of mathematics. We're going to actually discuss a slightly different meaning, though, than the one who knows. We're going to look at the geometric side of things. So we're going to look at a lot of similarity today. So we know from geometry, two objects are said to be similar if it is a scaled version of the other. So think about an old times slide projector. When you put in a slide, project it onto a screen. That's obviously a similar image. Probably a more relatable comparison to make would be that when we were in class, obviously I had my iPad. I was airplaying that to the projector screen. And so you were seeing a larger version, but a similar version of what I had on my iPad. So obviously photocopies, things like that, are also examples of similar figures. To get a little more in depth on triangles, we're going to say that two triangles are similar if and only if the measures of their respective angles are the same. So looking at these two triangles that we've got, we're saying that the measure of angle alpha over here on the left is the same as angle alpha over here on the right. And then the same with beta and beta and gamma and gamma. Alternatively, you can also say two triangles are similar if and only if their sides are proportional. What we mean by that is that they are different by some constant k. Meaning that if you take c and multiply by k, you get kc, and then if you multiply by k with all the other respective sides, you get to a triangle that is proportional to the first. So two different ways to think about similarity. One is having all the same angles, the other is having proportional sides. When we talk about similar figures, we can also talk about squares and rectangles. For instance, two squares will always be similar. If you think about two squares, every single angle is going to be 90 degrees, and all sides are the same length. And so really, with squares, pretty easy to make that jump to saying that all squares are similar. Rectangles is a little bit harder. Now again, you still have all these angles the same. So remember, in a rectangle, you've got all 90 degrees, but they have to have corresponding sides that are proportional, meaning that in this example, S and KS are proportional, L and KL are proportional. So you almost have to think about this rectangle being kind of turned and flipped around to mirror this one. Okay, and then last but not least, let's talk about circles, discs, and rings. So circles are always similar. So when you think about a circle, you're thinking about just that part right there. So really that line doesn't have any depth to it. It's as thin as can possibly be, but two circles will always be similar. A circular disc will always be similar to any other circular disc. So the only difference is that is now a circle plus all of its interior. So think about the circle plus everything else that is kind of filled in there. The last is circular rings, and this is where you have to be a little bit more careful with what is similar. Two circular rings are similar if and only if their inner and outer radii are proportional. So by inner radii, we're looking in this case at the distance from your center to the kind of inner part of your ring, and then same here, center to the inside part of your ring. That also has to be proportional from the center to your outer part of your ring, and then again from the center to the outer part of your ring. So you have to be a little bit more careful with circular rings than you do with circles and with discs. So in geometry, we're going to say that a gnomon, G to a figure A, is a figure that, when suitably attached to A, produces a new similar figure to A. By attached, we mean that the two figures are coupled into one figure without any overlap. So we're kind of thinking about how they could kind of perfectly fit to one another. To give you an example, kind of informally, we'll describe it this way. G is gnomon to A if G and A is similar to A. So if you think about here, we've got this symbol A. If we attach G to A, as you see over here, then what we're saying is that this first figure, figure A, is similar to this figure G in A. In other words, we're saying that this angle is proportional to this angle, that your two bottom angles, two base angles, are proportional to these two angles here, and that obviously the sides are also proportional, so that this side is proportional to this side, and so on and so forth. For gnomons to squares, if we have a square S, then you have an L-shaped figure that would be considered the gnomon to a square. And you can see that when attached to that, G is attached to S as shown, then you get a square, they're calling it S prime, that is also similar to S, meaning that all the angles are still right angles, and obviously what they're doing is just increasing by this distance on one side, this distance on the other side, to still get a square where the sides are the same length. Lastly, to talk about circles, gnomons to a circular is a circular disc with a radius r. So when we're looking at O-ring G, so this O-ring G with inner radius r is a gnomon to C. In other words, if you put C and G together, you get C prime, which is going to be similar to your original circle C. And again, that's just because all circular discs are in fact similar. Last but not least, gnomons to rectangles. Consider a rectangle R with a height h and base b. The L-shaped figure G can clearly be attached to R to form a larger rectangle. It does not in and of itself guarantee that G is a gnomon to R, so you kind of have to be careful with that. We're going to have to look at how h plus x compares to h and how b plus y compares to b. So a rectangle, R prime, is similar to R if and only if their corresponding sides are proportional, which means that b over h has to be congruent, or it has to be equal to b plus y over h plus x. With a little bit of simplifying, you can say then that b over h has to be equal to y over x. So a simple geometric way to determine if an L-shaped G is a gnomon to R is to just extend the diagonal of R and G and R. So if you extend the diagonal that passes through the outside corner of G, then G is a gnomon. If it doesn't, then it isn't. So the example on the left side here, basically all they did was they took this diagonal that originally only went this far, extended it, and it still went through the corner. But in this next figure, when they extended that same diagonal, it now is missing the point that it's supposed to be going through. In other words, over here we have a gnomon, and here we have one that is not considered a gnomon. Okay, so now we're going to talk about a special triangle, and we're going to talk about what's called the golden triangle. So let's just start with an isosceles triangle T. You've got vertices B, C, and D, and the angles measure 72 degrees, and 36 degrees. And those were chosen on purpose, so those were not chosen arbitrarily. On side CD, then, what we're going to do is we're going to mark the point A such that BA is congruent to BC. So we're going to connect kind of a new triangle here so that these two sides are congruent, which is what they've done over here for you. So looking at that, now you have a new isosceles triangle, which means that this 72-degree angle should now be the same as this new angle that we've formed, BAC. And then we also are cutting this angle in half, so 32 degrees is now, or 72 degrees is now 36 degrees. So again, this kind of talks you through all that I just mentioned to you. So this implies that triangle T prime has equal sides, or has equal angles. So if you look 36 and 36, and then obviously the 72s and 72s, so these are similar triangles. So in other words, we would say that BDC is similar to CBA. And it's probably been a while since you've seen that notation, but just remember that if you want to say that they are similar, this is the way that we do that. Remember, congruent, slightly different. You've got the equal sign with the tilde above it. That actually means that they are the exact same size, in addition to having all the same angles. So, who really cares, you might ask? Where's the gnomon to triangle T? We don't have it yet. We're going to get that gnomon to triangle T. It's actually going to be triangle BAD, labeled G prime. After all, G prime and T prime is a triangle similar to T prime. Notice that G prime is also an isosceles triangle. So you've got this side congruent to this side. So now your angles are 36 degrees, 36 degrees, and 108 degrees. So slightly different angle measures this time. So we now know how to find a gnomon, not only to triangle T prime, but also to any 72, 72, 36 triangle, including the original triangle T that we had. All you have to do is attach a 36, 36, 108 triangle G to one of the longer sides of T. If we repeat this process, something kind of cool happens. You get this kind of spiraling effect where the triangles continue to get larger and larger and larger. It's not too far-fetched to use kind of a familiar analogy. If you've got triangles T and G that are the parents, with T having the dominant genes, the offspring of sorts of their union looks just like T, but a little bit bigger. The offspring then has its own offspring, and you continue and continue and continue. So this actually gives us an example of two triangles that are very special to us. These are examples of what are called golden triangles. So these are the only two actually isosceles triangles with these property. So no matter what you tried to do, no matter what angles you tried to use, the only two triangles that have this property are 72, 72, 36, and 36, 36, 108 degree triangles. And in fact, even more so, the reason why we call them golden triangles is that the ratio of their sides is actually the golden ratio, which is kind of an interesting thing to think about. So in a similar way, let's kind of talk about square gnomons to rectangles. So if you've got a rectangle R with a side of length L, so the long side, and S being the short side, and suppose the square G has a side of length L, is a gnomon to R. So in other words, what we're saying is that they are the same length down here. So when you attach them, we should have a gnomon. So if so, then your rectangle R prime must be similar to R, which implies that their corresponding sides must be proportional. And so the long side of R prime and short side of R prime are equal to the long side of R and the short side of R. After some algebraic manipulation, this equation can be written now in the form of L over S squared is equal to L over S plus 1. And since L over S is positive, L and S are the side lengths of a rectangle, then this last equation essentially shows that L over S that satisfies the golden property, so remember that you've got this golden ratio, and the only positive number that satisfies the golden property is our number 5 that we came up with in our previous lesson, and so this is our conclusion. So we can summarize all of that with the following conclusion. A rectangle with sides of length L and S, being the long side and short side respectively, has a square gnomon if and only if you have the L over S is equal to 5. And a rectangle whose sides are in proportion of the golden ratio is going to be called a golden rectangle. So far we've had golden triangles, and there's only two of those, which were the 72, 72, 36, and 36, 36, 108s. It actually turns out that there are an infinite number of golden rectangles. So we're not as limited by those restrictions, as long as they satisfy that relationship that L over S equals 5. A close relative to a golden rectangle is what's called a Fibonacci rectangle. And the only difference is that a Fibonacci rectangle is a rectangle whose sides are consecutive Fibonacci numbers. So looking at golden and almost golden rectangles. This rectangle on the right has a length of 1 and a shorter length of 1 over 5. And since L over S would be equal to 1 over 5, then what you can do is take the reciprocal of the denominator, so 5 over 1, which is just 5. In other words, this would be an example of a golden rectangle. So, another example. This rectangle has a length of L is equal to 5 plus 1, and the shorter side length is equal to 5. So that gives us that L over S is equal to 5 plus 1 over 5. And we know from our notes from Tuesday that 5 plus 1 is the same as 5 squared. So this would be the same as saying 5 squared over 5, which ends up reducing to just be 5. So this is actually also a golden rectangle. To look at another example here, we've got a rectangle that has a length of 8 and a side of 5. Then this would be what's called a Fibonacci rectangle, since 5 and 8 are consecutive Fibonacci numbers. So remember Fibonacci numbers: 1, 1, 2, 3, 5, 8, 13, 21, and so on. So because these are two consecutive Fibonacci numbers, that's what makes this a Fibonacci rectangle. The ratio of the sides then, if you take L divided by S, would be 8 divided by 5, which is 1.6. So, not quite a golden rectangle, because 1.6 does not exactly equal 5. On the other hand, 1.6 is reasonably close. 1.6 is approximately, it's a little bit less than, but it's pretty close to what phi is equal to. And since it's close but not exactly, we'll have this notation and say that it's almost golden. To give you another example, this rectangle has a length of 89 and a shorter side length of 55. It's also a Fibonacci rectangle, so much further down on the list of Fibonacci numbers. The ratio of sides in this is L divided by S is equal to 89 over 55, which is 1.6181818. In theory, this is not a golden rectangle, so technically speaking, not golden. But in practice, this rectangle is about as good as it gets. Again, theoretically, you have to get to a infinitely large pair of Fibonacci numbers in order for it to be truly golden. But, when it's golden ratio up to 3 decimal places, usually we say that's about as good as it gets. To show you where these show up in the real world, you might be wondering, well, that's all cool and great, but why do we care? It turns out that you probably see golden rectangles more than you think you do. Next time you're down the cereal aisle, take a look at the cereal boxes, and if you really wanted to check them out, what you can do is measure those boxes. For example, Kellogg's Corn Puffs have a shorter side length S of about 7.44 inches for the regular size box, not the jumbo box that you get at like Sam's Club or Costco. And then they have a longer length of 12. And if you take 12 divided by 7.44, not surprisingly, it's very, very close to that golden ratio. So, just kind of interesting how that works. It actually is not a coincidence. It's actually a design perspective that we've been kind of accustomed to seeing things that are golden rectangles as being kind of the ideal rectangle. So actually when people are designing products such as, TV screens, when they're designing cereal boxes, movie posters, what they're actually trying to do is they're trying to get those to be proportionally golden rectangles. The idea being that golden rectangles are kind of the perfect in-between. They're not too skinny, they're not too kind of squarish, they're kind of that nice, kind of ideal rectangle that you'd want to see. Which leads us to this golden ratio hypothesis, which basically states that human beings have an innate aesthetic bias in favor of golden rectangles, and so our appeal to our natural sense of beauty and proportion leads us to these golden ratio type rectangles. All right, a little bit longer video today. Thank you for watching all the way through. If you made it this far, don't forget, guys, that on Friday this week, I'm going to have a quiz unlocked for you on Unify. I'll have some more instructions that are posted later today on how to access it. It will be available from 8 a.m. tomorrow morning until 4 p.m. tomorrow afternoon, in case you'd like to check out and test your knowledge of what we've been talking so far this chapter, and then we will start chapter 14 next week. I've got one more video to post for this chapter. It should be up shortly for you. Have a great rest of your day, guys.